Okay, so for the first practicum, maybe you guys already know the procedure, but I'll mention it again briefly. So we would have 6 practicums throughout the course, and the setup is that around 1 week ahead, I will post the practicum online, and then you have 1 week to work on it, and then in this time slot, we will go through the solution together. So this is not mandatory, so it's for your own understanding and practice. And it will not be graded, so I guess no stress on it. You can also finish it later after you understand more in this solution session as well, but yeah, nothing is mandatory. So yes, first practicum on simple neural network. So in this practicum, we will together build a perceptron model, as you have seen in the lecture. And then we will also build a multi-layer perceptron from scratch using NumPy. So this is also for you to understand deeply how does this work, like how to initialize weights of the model, how to do forward pass and backward pass, how to calculate the gradient, and how to update the weights. So, but in practice, people usually use PyTorch, and with this, it's going to be much less implementation effort because most of the stuff would be done for you already by PyTorch. But yes, we will go through both ways to gain more knowledge for you. So the first challenge that we will try to solve is the XOR task that you have seen in the lecture. And then we will move on to classification problems using the iris dataset. So for exercise 1, XOR task, so probably you already know, but I will briefly explain it again. So you will have 2 binary input, and if only one of the binary input is positive is 1, then the output would be 1, and otherwise the output would be 0. So here you have 2 binary input and 1 binary output. So here come the solution. So we import NumPy, nothing special about that. So first we will try to build a perceptron, a single neural, which takes 2 binary input and output 1 binary output. So as you see here, we have 2 input, and then we do a weight sum of the 2 input, and then we have an activation function, and here's the output. So yes. For this exercise particularly, I have provided you with the perceptron update rule. We didn't go through this in the lecture, I guess, so you can just take it for granted and use this formula to update the weight of the perceptron. Yeah, so here's the formula. At every step, you update the weight of the perceptron by a delta value, where you multiply the learning rate with the target minus the output, and then multiply by the input, the corresponding input. So yes, so here our activation function would be simply outputting 1 if the weighted sum is positive, and outputting 0 if the weighted sum is negative. And here's the implementation. So first we have to initialize the weight of the model. Here I just simply initialize everything to be 0. So the weight of the neurons should be 2 because we have 2 input. The bias also initialized to be 0. In the forward pass, we just do dot product of the weight and the input, and then plus the bias, which is according to the formula. And also, and next is the activation function, outputting 1 if the output is positive and 0 otherwise. Here we implement the perceptron update rule, which we take in the target, the prediction, the input, and the learning rate. So here's the update rule where the new weight is updated by this formula, where we increase it by the learning rate multiplied by targets minus output times input, which we have seen before. And during the training loop, we go through each sample individually. We do 1 forward pass to get the output from the input, and then we do 1 perceptron update round from that. During inference, we would have a list of input, and then for each input, we do 1 forward pass, and then we append it to the output, and then we return the output. Yeah, so that would be the basic implementation of the perceptron. And next, we just use it by initialize this class. This is our input data. As I have shown in the table in the beginning, it's going to be 00011011. and then the corresponding output for the XOR task. And then we train our perceptron, and then we perform prediction. So, yes. And then for evaluation, you were asked to implement accuracy, but I guess accuracy is quite simple to grasp, so I guess I don't have to explain too much on this. So here we just simply compare our prediction to some certain threshold, which you can tune yourself. And if it's bigger than the threshold, then we output 1, otherwise we output 0. And then we calculate the accuracy on the output of our perceptron. And as you have learned in the lecture, well, perceptron can only solve linear separable problems, which XR is not. So you will see that whatever you try to do, increase the learning rate, decrease it, train it for longer, you will not be able to get to 100% accuracy on this task. So yes, I guess that's basically it for the first exercise. Any question so far? Okay, then we will move on to the second exercise, XOR with MLP from scratch. So I guess this is the most implementation heavy task of this practicum. But keep in mind that in the future, if you actually work on this type of stuff, you would use PyTorch mostly. So in real life, it's not going to be that much implementation issue. It's just for you to understand how things work. So yes, so you, as we talked about in the lecture, multi-layer perceptron can deal with non-linear separable problems. So it should be able to solve our XOR task. So this is the architecture of the MLP that we will try to implement. So again, we have 2 input and 1 output, and we will have 3 hidden layers fully connected. And for each layer, we will have 3 neurons. So the first task is to initialize the weight. And here we use Xavier initialization. And here I already provide you with the formula for it. So we're just gonna apply it to our code here. So for this, we take in the input side and the output side of each layer. And then we calculate the bound according to this formula. This is basically just implemented out. And then we initialize the weight by doing uniform distribution, where the lower bound and the upper bound is defined by this number here. And then the shape of the layer should be input side and output sides for obvious reason. And then we return the weights. The next one is to implement a feed-forward layer. So it simply just apply a linear transformation to the input X using a weight matrix W and a bias vector V. So this is the formula, and this is the derivative, which I guess you also have learned in the lecture. But yeah, so basically this the derivative with respect to the weight is going to be the corresponding input. The derivative with respect to the bias is going to be 1. And the derivative with respect to the input is going to be the corresponding weight. And here comes the implementation. So for initialization, for the weight, we would use the Xavier initialization that we just implemented before with the input side and the output size of the layer. The bias, I initialize it to be all 0, but I guess you can also try different types of initialization. For the forward pass, it's just a dot product between the input and the weight plus the bias, nothing special. And here we have to save the input X because we will need to use it later on when we calculate the derivatives in the backward propagation. So this is the backward pass where we take in D values, which is the derivative of the upper part of the neural network. And then we also take in the learning rate to see how much we're going to update our weights. So yes, so here we have to calculate the derivative with respect to the weight, where we just multiply the input with the upper derivative. The weight with respect to the biases is just going to be the sum of all upper derivative, because for the bias vector, the derivative is going to be a vector of all ones. So when you do dot product, it's just going to be the sum. The weight with respect to the input is gonna be the upper derivative multiplied by the width. And then we update it according to the learning rate, where we update both the width and the biases of the layer. And then we return the derivative with respect to the input so that we can use it later on to pass it down and update the lower part of the neural network. So here I have a question. Why do we need to calculate the derivative of weights, biases, and also the input? So I guess this is also something that you already got the answer from the lecture. We need to calculate the derivative of the weight and the biases to update them and of the input in order to backpropagate to the lower part of the model. Any questions so far? Okay.
I have one. Why do we need to calculate the derivative of the bias if it's set above that the derivative of the bias is 1?
The derivative of the bias is 1, but then we how do I explain this? But then the bias itself still contributes to the output of the neural network, so it's like a learnable weight. So it's still we still have to multiply it by the upper derivative, and then you will see that the derivative of the biases is not going to be always 1. It's going to be dependent on the upper derivative. So you still have to change the biases by a certain amount at every step. So it's not going to be fixed. Moving on. So here we will add nonlinearity. As you have remember from the lecture, if we don't have any nonlinearity activation function between the layers, then it all can just be collapsed into one single linear layer. And then it's destroy the purpose of having a more complex neural network to solve our problem. So that is what we're going to do. Here, you were asked to implement ReLU, which is a simple activation function, which is like a combination of two linear functions where it output all 0 if the input is negative and doesn't change anything if the output is positive. So the reason why ReLU is sometimes favorable is that it's quite simple. It's just a combination of two linear functions. And also it's quite easy to calculate the derivative of ReLU. As you can see here, if we calculate the derivative with respect to the input, it's going to be 1 if x larger than 0 because the function is x. And it's going to be 0 if x is less than 0. So calculation and implementation should be relatively simple with this activation function. And as you can see here, it's quite a short implementation. The output is just going to be the maximum between x and 0. Again, we have to save the value of x because we need to use it in the back propagation. In the backward pass, it's just the upper derivative multiplied by the derivative of ReLU itself, which is 1 when is when the input is larger than 0 and 0 when the input is negative. And we return this in order to backpropagate to the lower part of the model. So next we will move on to backpropagation. So as you see before, for the simple perceptron, we have this perceptron update rule. But then for this complicated MLP, there's no such straightforward rule that is promised to converge like that anymore. So we have to do backpropagation. So just calculate the derivative back to the input and then update the corresponding weights. And for this, we need a loss function. And here we use binary cross entropy because for this XOR task, the output is binary. So it fits the task. This is the formula you have learned in the lecture, and this is the derivative. Here I also took it for granted, but if you want to look into details how this was calculated, then you can just click on the link. I don't remember if I put it into the notebook itself, but I will make this solution notebook publicly available later, so you can just look at it at your free time if you want to. Yes, so in the forward pass, I take in the output and the target, and then just implement this formula, nothing special, then return the loss. And in the backward pass, also need to take in both the output and the target, and then implement this formula. Yes, so that's all for loss function. Okay, next is sigmoid activation function. So before for the nonlinearity, we were using ReLU in between of the linear feed-forward layers. But for the final output, because here we have a binary classification problem, we would ideally want some output that is clamped between 0 and 1. And then we can interpret that value as the probability of the output being positive or negative. So that's why we're going to use this sigmoid activation function. I mean, this is also a nonlinear activation function to add the complexity to the model. So you can also try this to replace ReLU to see how the network behaves. But according to my experience, then for this task specifically, if I use sigmoid in between as well instead of ReLU, then it seems to converge slower. But yeah, you can try everything. It's just a hyperparameter choice. Yes, so this is the formula for the sigmoid function, and this is the derivative. Again, the derivative is not that straightforward to explain, but if you want, you can just look at the math at your free time. So for the implementation, I have this function that take in x and then just calculate the sigmoid function. And here I have the class sigmoid activation function. Again, have to save the input x so we can use it later. And the output, I just calculate the sigmoid over the input x and then return it. In the backward pass, I just multiply the upper gradient with the derivative of this activation itself. So this is basically just the code right out of this formulation here. So I guess that was all of the components so far. Any question? Yes.
What is D values?
Sorry.
What are D values?
D values is the derivative of the upper part of the neural network. So because we use the chain rules, every time we calculate some derivative, we multiply it with the part beforehand. So yes. Okay. And now we will move on to the implementation. So it's just putting everything together in the initialize part of this class. We initialize the number of hidden layers, size, the activation function, which is ReLU or sigmoid, loss function, output activation function, layers, and here we save all layers to a list for convenience. Yes, so for initializing the layer, for the first layer, the only different thing is that the input size of the layer should be the input size of the network itself, which is 2 in this case. And for all other hidden layers, it's going to have input size 3 and output size 3. It's just our choice of architecture. And then we append all of those into our layers, into our list of layers. And then the last output layer is going to have the hidden size as the input size, and then the output size as like the final output size, which is 1 in this case. Yes. In the forward pass, we just go through each layer one by one. We do forward pass through the first layer and then pass through the hidden activation function, and then again to the second layer, hidden activation, third layer, hidden activation, and then last layer, and then last output activation function, which should be sigmoid in this case. Backward pass, we do it reversely. So D values here, the first D values, the first derivative we have is going to be of the output activation function, which is the sigmoid. So we just do backward over the activation function of the output layer, and then we backward through the output layer itself, and then go in the reverse direction. So here we reverse the list of layers, and then go through each layer, and then hidden activation itself, and then just back to the beginning of the input, so that we have the derivative of every single weight, so we can update them later on. Here is our training loop, where we take in the input data, the target, learning rate, and epochs. So for each epoch, we would try to iterate over all samples in our training data. And here I just use stochastic gradient descent, where I randomly draw in each step, I randomly draw a sample and then update the whole neural network according to that layer, according to that sample. So here I just do random order shuffling of the training data and then, yeah, update them one by one. So first thing is to do the forward pass through the whole network, get the output. Then we calculate the loss because we have the output and also the target already. And then we do backward pass where we calculate each derivative in the backward direction. And then update the weights according to the learning rate. During inference is similar to the perceptron that we talked about before, just have a list of output and then go through every single samples in the input inference data, and then we return the output. So yeah, any question? Okay. So next we will use our implementation. For this one, we just initialize an instance where input size 2, because as I explained before, output size 1, hidden layer size 3, number of hidden layers 3, and then hidden layer size 3. Hidden activation function to be ReLU for simplicity, output activation function to be sigmoid, so we can have a probability between 0 and 1. Loss function binary cross entropy. And then we do training with input and targets data similar as before, and then we do our training data. Here I set the learning rate to be 0.05 and 3,000 epochs. But I guess you can play around with these hyperparameters to see how the network behaves. And I find that if I choose a much smaller epoch, then the model failed to converge. So this is what I chose. Also because we have such a small data size here, because for the XOR problem, we only have 4 data points. So I have to do extra amount of epochs so that the model can have enough update rounds. So evaluation, we just do inference on the input data and have to do some reshape to just implementation details, and then calculate the accuracy. So for this MLP, I was able to reach 100% accuracy. So it proves what you have learned in the lecture, that MLP is capable of solving nonlinear separable problems, unlike the single perceptron. We also have this demo for you to see how the decision boundaries are found by the MLP, and you can look at that and play around with this, change the number of hidden layers and size and all hyperparameters to see how it works. But yeah, so I guess that's all for exercise 2. We'd implement everything by hand. So any question? Okay. Now we go to the third exercise, which should be less implementation effort, but then more documentation reading effort, I guess. So as I mentioned before, not everything, like most of the heavyweight implementation details is going to be handled by deep learning framework like PyTorch. You can also try TensorFlow, but for that, I don't have as much experience, so I'm afraid that I wouldn't be able to help you as much. But there are frameworks like that to help you with the basic implementation of forward and backward pass for commonly used functions like feed-forward layers or sigmoid or ReLU. Yes. So to define the model, we will try to build exactly the same model which we have implemented before with NumPy. And here we will use NN.sequential to just as a wrapper around all of our linear feed-forward layers. So same as before, input size 2, and then all the hidden size going to be 3, and then ReLU activation in between, and sigmoid in the end. Initializing weight, PyTorch also provide this Xavier uniform initialization. So you also don't have to implement that yourself. So here I just take the whole module and I go through this list one by one, and I see if it is a linear module, then I would initialize it with this Xavier uniform. And again, here I also implement initialize the bias to be all 0, which is consistent to our implementation before. Loss function binary cross entropy also implemented by PyTorch. So I guess this part is just mostly for help you with experiencing with finding documentation of a particular framework. And here optimizer, we also do stochastic gradient descent as before. And also here they are implemented for you already in PyTorch. Learning rate 0.05 to be similar as before. Okay, now come to the training part. Should have put this later. Okay, so here, because we will use PyTorch and not NumPy anymore, so all of our vectors and matrices, we're gonna define it as a torch tensor instead of a NumPy array. But the content of is gonna be the same. So training loop, we put again to be 3000, and then we again loop through all epochs. And here are the training steps. We do first optimizer.0grad, and then we do this forward pass, calculate the loss function, do backward pass, and then do optimizer.step, which is supposed to update the weight of your model. And here I ask you to print out some of the weight and some of the gradient just to see what happened. So here I just print out the weight and the gradient of the first layer to see what happened. And as you can see here, after 0 grad, the gradient would be none. So here we can see that the optimizer.0 grad is gonna erase all of the gradient that you have calculated before, and yeah, freshly store new ones. After the forward pass, nothing changed because you just calculate the output. After the backward pass, you would have the gradient for all of the weights. After weight update, this one is probably optimizer.step, then you would see that the weight of the linear layer here have finally changed. And then we do 0 grad again, and then erase all the gradients again. So this is the second epoch. Yes, so to answer my question, explain what happened after each step and why do we need optimizer.0 grad. So yeah, this one I have already explained. So we need to use optimizer.0 grad to erase the gradient because we already updated our model according to the old gradient. So in the next step, you would preferably not to use the gradient again. And sometimes it is useful to leave out this 0 grad. For example, if you want to train something with a huge batch size, but then it doesn't fit into your GPU memory, then you can do multiple mini batches, and then you accumulate the gradient, and then you update your model at once at the end of the batch. So you only do optimizer.0 grad at the end of the batch, so you can accumulate all the gradient of the mini batches. Yes, that is in theory. Here we are not doing batching in our implementation, but yes. The next question is to follow the loss in the backward direction to see the computation graph. So here we can use graph.fn, and we see that if we backward through the loss to see what happened, to see how it was calculated, we will see that it was calculated lastly using the binary cross entropy. And then sigmoid, which is the last thing that was used to calculate the loss, which is the output activation function. And then it was the module. And here, if we do further backward, it wouldn't show anything because we already wrapped all of our linear layers into one module. So this is the furthest you can see. But if you don't wrap it into the module dot sequential, then you would be able to see the whole path of the graph if you do this. But yes, this is for just for debugging purpose or for you to understand how everything is calculated. Okay, next on evaluation, same as before, we just do one forward pass through our input data, and then we get our prediction. We pass it to our accuracy calculation function with the output, the target. And then here we include a threshold of 0.5. And as you can see here, I again achieve 100% accuracy on the simple XOR task because NLP is complex enough to solve it. Here we have to do prediction.detach.numpy because, well, it was a torch tensor, and then it was connected to a whole computation graph in PyTorch. So if you just pass it as is into this accuracy function, there's going to be some typing issues. So you have to do detach so that you only get the values of the output and not the whole computation graph. And .numpy to convert it to numpy again, then you can pass it to our accuracy function. But yeah, I guess that's it for the third exercise. Any question? Yeah.
Is there some way to visualize the computation graph, or to do it like a little bit more complex than just printing the function?
Yeah, I Googled it, and I think there is this graph viz library or something, and then you can just pass in this, and then they will visualize it for you as a PDF or yeah. So I haven't tried though, but I guess it should work. So okay, moving on. So our last exercise is to do some classification tasks using MLP with PyTorch. So Iris is a data set containing information on flowers where the features, where they have 3 features, I think: the length, the width of the sepals, and the petals. Okay, so I guess 4 features. And then there's 3 output classes, which I'm not sure how to pronounce, but yeah, there are 3 classes. So in this exercise, we will also see how PyTorch can help us to use GPUs batching to speed up our training process. And here you can just use the GPU provided by Colab. But I guess it's quite straightforward to follow this code, but just one small remark that if you use this freely available Colab GPUs, then maybe it's good to disconnect it whenever you stop working on the exercise, because if you leave it on, then it got subtracted to your hours of using GPUs, and then at some point they will forbid you to connect to it, and then it might hurt your progress. So yeah, just a side note, because in the future, probably we'll also use this Colab GPUs for simplicity, so we don't have to provide you with online GPU cluster or whatever. Okay, so loading the data set. So this is already available in scikit-learn. So if we load this data set, we would already have the data and the target in numerical values. And there would be 3 classes. And your first task is to process the data. So here we will split it into train and test. Here I just use the sklearn train test split function, but you can also do this manually and do it randomly. Doesn't matter. The next step is to convert anything into tensor, because as I mentioned before, everything needs to be, every array and matrices needs to be in tensor so that it works with PyTorch. That. And another thing is that we want to convert the target into one-hot encoding. So in this data set, I think the original label was 0, 1, and 2. And we can, in theory, just use them directly and then treat it as a regression problem. But the thing is that in that way, each label is not going to be treated equally, because the model can infer that class 2 is 1, so it should be larger than class 0. So we would like to have a way to equally treat all the classes. So by one-hot encoding, every class is going to be a vector where only one item is one. So they are basically treated equally by the model. So we will again use MLP for this task with PyTorch. And here I ask you to initialize the model with 4 hidden layers and a hidden layer size of 768, which I guess is a bit overkill because it's quite a big model size to solve this small task. But I was trying to show you how much GPU and batching could help you with speeding up the training process. So I set it as this big model size. If we have a smaller model size like earlier with hidden layer size 3 and also 3 layers, then it actually doesn't make that much sense to use GPU and batching for training because the communication overhead between CPU and GPU is gonna be not worth enough to speed up the whole thing if your model is too small. So here I just use the bigger model for demonstration. But in reality, I guess if you have a simple task like this, it's better to use a smaller model for to save computational resource. So question, what should we change on our model to make it fit this task? So one thing that you have probably noticed is this no longer a binary classification problem because now we have 3 different classes. So one thing we have to change is that the output size should be 3. So we should have the probability for each class rather than just single ones like before. Another thing is that we should change the loss function. Here we use cross entropy loss and no longer binary cross entropy loss. So there's 2 ways of doing it with PyTorch. Just input raw logics into this cross entropy loss function, or we normalize the output into 0 and 1 with log softmax, and then we pass it to NLL loss. So yeah, this is just PyTorch specific, and I guess you can read up about it in the documentation. But yes, so we have the we have similar way of building the model as before, put all the linear layers into this sequential module, initialize with the same way, initialize the loss function and initialize the optimizer, given the learning rate. And then in the exercise, I think I already provided you with a simple training loop. And with simple training loop, I think by default, PyTorch would just use CPU for training. And here with 500 epochs, what I achieved after this whole training process is that it took around 14 seconds. But what you can do is to use GPU by moving everything to GPU. So this device here we have set earlier when we initialize the, when we start using the GPUs, where we set the device to do torch.cuda.current device. So it's going to be the GPU instead of CPU. So if we want to use GPU, the first thing is to move the model itself to the GPU. We have to move input training data to the GPU and also output training data to GPU. So move everything to GPU. And then the next question is to do batching. And here we make use of tensor data set where we just pass in our training and training data and set the batch size. And then we create a data loader given the batch size. So PyTorch just take care of it for you, so you don't have to implement everything into much low level. So same thing again, I set the timer before and after the training loop. Here, instead of iterate over every single sample, we iterate over each batch. And also do forward pass here, and then calculate the loss, and then backward and optimizer.step, similar as before. So with this batching and moving everything to GPU, I was able to achieve 3 seconds training time rather than compared to 14 seconds as before. So this is just to show you how much of the speed up you would be able to obtain with GPU and batching. And I guess the bigger your model is and the larger your data set is, you will see even more drastically improve in training time if you use GPU and batching. Okay, evaluation, same as before, prediction by doing one single forward pass through the input test data. Again, have to put it to device to GPU so you can make use of it also during inference. And then the prediction would be the biggest. So your output would be a vector of size 3, and then your final output class should be the biggest values, should be the index of the biggest values with within that output vector. And then same before, we have to move it back. We have to move the output back to CPU, convert it to NumPy, and then you're able to pass it into the accuracy function. Compare it to the goal test target, threshold 0.5, and then we have the accuracy value of 0.75, which is relatively good. I haven't tried to use different hyperparameters or increase the layers or using different activation functions. So maybe potentially we can get better scores than this, but this is just to give you an idea. Okay, last question. It's just to print the confusion matrix using scalar. And yeah, here we also just pass in the output and also the target, the goal target of the test set. And here's the output. And as you can see, most of the values lies to the diagonal part of the matrix. So the model is doing quite well. And the only mistake it make is here, where it should have predict. Okay, I don't remember how the dimension works with the confusion matrix. So it seems like it should have predict in class 1, but then it predicts class 2 instead, or the other way around. I'm not too sure. But yeah, so with this confusion matrix, you can see exactly why the model make mistake and maybe look into more details and do more error analysis. So I guess that's it. Any question? I will upload this later, so you can also go through this at your free time. And if you have any question afterward, you can always feel free to post it on Elias, and then I will take your question offline as well. So yes. If there's no question, I guess we can do an early break. Yeah. Okay. Thank you for your attention. Mm-hmm.